And yep, okay, recording in progress. That's good. Hi, I'm back.
Daniel, you disappeared. Yes, we can see you.
For some reason, the recording kicked me out. Good, that's a great start for the presentation. Okay.
No problem. Okay.
So
Whenever you're ready. Yes.
Yes, yeah, all good. So, hello everyone. Once again, hopefully I will not be kicked out again. I just wanted to add to Clara's great introduction that for me this opportunity is really special in a way because I was also part of the academy. I was part of the 6th edition of the academy back in 2019. And back then we were only 6 people receiving these lectures and this education part. So it makes me really happy to see that now we have a new format that allows us to reach out to so many people in so many different locations. So that's really great. And just adding on that, I was back in 2019. I was in a very similar situation as you are. I was just recently graduated from architecture school, and I had some knowledge about environmental design and weather and climate and so on, but it was actually very limited. So I did learn a lot through the academy program, and later on I had the opportunity to remain in to continue working in Transsolar and like to expand those knowledge. So um, saying that please feel free to interrupt me at any time. Some of the concepts and principles we're gonna cover today can be a bit confusing at times. So we're gonna try to make this lecture very informal, and so interrupt whenever you want. And if something is unclear, we can just revisit it and hopefully explain it in a better way. Okay, so I'm just gonna start sharing my screen so we can begin with the lecture. Give me a second. So that will be screen 1. Okay. And we need to go full mode. Just a second. We need to change. Yeah. So you guys please confirm that
Yes,
you're.
Daniel.
Yeah, perfect.
We see it perfectly.
All good. So let's set the laser point. You guys can also see this?
Yes, we can.
Yeah, perfect. Okay, so we're all set. I would like to start the presentation with this amazing phrase that I found while preparing the lecture. Unfortunately, I couldn't find the name of the author, but I think it's really powerful. And as we move forward with the presentation, it will hopefully become clearer why I really like this phrase. So it says, light is a curious thing. You cannot feel it, you cannot smell it, you cannot hear it, but you can definitely see what it does. So when we think about light, most probably to all of you, what comes to mind are sources of light, right? When we think about light, we think of a bulb, we think of the sun, we think of a flashlight or a fire, but this is not technically light. This is more these are more sources of light, and sources of light in general can be divided into 2 um, main categories. So there are natural light sources and artificial light sources. So let's start by covering some of them. It is impossible to talk about light without talking about our sun. So the sun is the major source of light for our planet. It produces massive energy because of the nuclear fusion that is happening at its core, and these reach out to Earth in the form of light and heat, right? And this is essential for the sustainability of life in Earth. And it produces one of the most beautiful phenomenons in our planet. right? So that's why it comes with no surprise that human beings, as in many different civilizations, we have been worshiping the sun, and this you can see in different cultures all across the planet, from Native Americans to the ancient Egypt, and so on. So of course, the sun, it's not the only source of light, natural light. Other stars, they also emit some light, only that which is called starlight, right? But the problem is that because of the distance they are from our planet, this light spreads, and that's why only a tiny fraction is actually reaching Earth, which can be something like 0.0000002%. That's almost nothing hitting the Earth. The moon is also a source, a natural source of light, only that the moon does not produce light itself, but rather reflects light from the sun. And this is due to moon having an albedo, which is the reflectivity of its surface, of around 0.12. This means that the moon reflects back 12% of all the radiation that falls upon it from the sun. So, and that's why it appears as it is glowing, but it's not producing light itself. Other sources of light can be lightning, which is can be visible as a flash of blue-white light, and this is due to extremely high temperatures, something around 25,000 degrees Celsius, which is basically heating air molecules to a state of incandescence. And this combined with nitrogen gas, which is also stimulated into luminescence, gives lighting this particular color. Volcano eruptions can also be a source of light because of the high temperatures that are being um, basically lava and other material that is being produced with a very high temperature. And in general, there are bioluminescence organisms which are able to produce light themselves, either through a series of chemical reactions or by a form of glowing bacteria, right? But we already covered some of the natural sources of light, but I just want you to think for a few seconds, which one do you think is the most commonly used artificial light source? So think of your daily life, think in history. Which one do you think could be the most commonly used artificial light source? And I know that many of you might believe, because it was also my belief before, that this will be a bulb, right? Or LED, but it's actually not. Actually, the most common artificial source of light is fire. And you might think fire, but fire is a natural phenomenon. It happens in nature, and yeah, fire can be both a natural source of light or an artificial source of light. The difference is what originates the fire. So if fire starts because of a lightning striking on grass, and then you have a wildfire, then this is natural. But if we start the fire, then it is artificial. And then evidence shows that humans have been using fire for over 500,000 years. So that makes it the winner compared to electric lights like light bulbs, which have been only around for a bit more than a century. The first light bulb was introduced in 1879. Candles are other artificial sources of light. Of course, light bulbs in all of their shape, either if they're incandescents, which is the one that that is commonly associated to a light bulb, or more modern and efficient source of light bulbs, which can be LEDs. And of course, flashlights, lasers, glow sticks, lighters, and even your mom's or dad phone screen with a brightness at the maximum can be a source of artificial light. So, but this is not light. Again, these are just the sources. So in order to understand what is light, we need to go a little bit into history of physics, and through history, figures like Christian Huygens or Isaac Newton, they did some research on light, and in fact, Newton was convinced that light was made of small particles, and while Huygens was believed that light was waves. But we're going to focus today in these three figures, which are James Clerk Maxwell, Max Planck, and Albert Einstein, because their ideas and theories evolve and have been proven to depict light itself. So let's start with James Clerk Maxwell and his theory of electromagnetism, so which is also known as classical electromagnetism theory. So basically, Maxwell depicts light as a transverse wave, which is composed of oscillating electric and magnetic fields. Yeah, as you can see in this animation. Now, these electromagnetic waves, they have different properties. And so, for example, one of the most important is their wavelength, which is basically the distance between their peaks, and then their frequency, which is how many of these oscillations happens within a unit of time, can be second, for example. And then the height, their amplitude defines their power. Okay, so the combination of different wavelengths leads us to the electromagnetic spectrum. So, and you might be familiar with the electromagnetic spectrum because we have found ways to give uses to the different properties of electromagnetic radiation in different wavelengths, like the X-rays or the gamma rays, or the microwave or the radio wave. So as the wavelength becomes shorter, we move farther into the ultraviolet spectrum and so on, and longer wavelengths, it's what we know as infrared and microwave and so on. Now, so all of this is light. Okay, so all of this is a form of light because all of these are electromagnetic radiation. But we only see, so human beings, we're only able to see wavelengths or electromagnetic radiation that it is between 380 and 780 nanometers. So this is what we know as visible light. Other species, for example, they have evolved into being able to see in different portions of the electromagnetic spectrum, which we can nowadays, thanks to advances in technology, we can use special cameras to have an idea of how these look like. Yes, somebody wants to ask something? Yep. Thank you. Just heard a microphone. Okay, so as you can see, butterflies, for example, they are able to see in ultraviolet, and then flowers. It's very different. Maybe we can go back once again to this nice animation. So this is how they will see a flower, and then flowers, they are communicating to the insects, so they look beautiful to us, but in reality this is essential for their metabolism and survival of species. So they're communicating, sending signals in just in different wavelengths that we cannot see. Or a snake, for example, this is how we see a mice, but this is how a snake will see a mice. Okay. Now, there are other response curves that are not necessarily related to species, but other to phenomenon. Like it can be, for example, this is the skin tanning electromagnetic response curve, or the photovoltaic, so that the photo effect in silicium can happen, which is this number 3 that goes from slightly 380 and up to almost 1000 nanometers. Now, the reason why we see light in this particular spectrum is not merely coincidental. You see, visible light, so light in this range, in this portion of the electromagnetic spectrum, is able to pass through the atmosphere and not being blocked. Where others like ultraviolet and X-rays and so on, they're blocked or absorbed by the atmosphere. For example, radio frequencies, there is also what it's called the radio windows, but the other portions might be blocked, but this is just an opening in the atmosphere, if we can say it in this way. But visible light is able to pass through the atmosphere, and farther than that, it's able, so visible light is the only set of electromagnetic radiation that propagates well in water, where most ice firstly evolved millions of years ago. So something very interesting happens because blue color is the one that reaches farther inside water, like roughly farther than 250 meters underwater, where red color is the first one to disappear. So if any of you has ever practiced scuba diving, you might be familiar with this effect. For example, this picture of a reef might seems purplish, but when you in natural lighting conditions, but if you illuminate it with a flashlight underwater, then you will see that it's actually more on the reddish color. So, and this is just because water is absorbing the red color, in this case, wavelengths that correspond to the red color, while blue is actually being scattered. And that's the reason why the ocean seems to be blue. It's just because it's being propagated in water particles. Okay. Now, if we, like I was saying, the initial forms of ice evolve in the ocean. And you can imagine how the ability of seeing light was very important for evolution, because you can gather information about the surroundings with almost no delay. So this was really, really helpful for survival of this species. And this led to our eye, so the human eye, which has evolved to be very complex and able to adapt to well-lit conditions and poor lit conditions. As you can see, so this is the human spectral sensitivity curve here in blue. This is our daytime um, uh, spectral sensitivity curve. You can see we have our peak briefly between green, what would be green or yellow color, while this shifts a little bit to the left, more into the ultraviolet part of the spectrum at nighttime. So we can adapt to poor light conditions. And then if we have a more detailed view into this, we can talk about photopic vision, which is in this case when we see under well-lit conditions, well, daylight, which allows us to perceive the surroundings in great detail. And then nighttime will be scotopic vision, which happens when there is not enough light. And basically, there are different cells in charge of for us to see, right, of the sight sense. And during nighttime, rods cells are taking care of forming images and rendering colors in our brains, for our brains, while cones are in charge during daytime. But this is very detailed. It would be really nice to have the time to dig deeper into this, but like in essence, this is what is happening. And then uh, different frequencies of wavelengths, they correspond to different colors. But the combination of all wavelengths results in the white color. So as we increase in the electromagnetic radiation frequency within the visible portion of the spectrum, we tend to see more green, blue, indigo, and violet, while longer wavelengths, they are mostly yellow, orange, and red. And that can be divided into the additive primary colors, so red, green and blue, and their combination. But you can see when we combine them all, the result is white. And so basically our eyes are, we have, most of us, we have 3 color receptors, which are able to detect these 3 main colors and the combination of them. So if we could take light and divide it using a prism, which Newton was one of Newton's discoveries, and other scientists back in the days, you could then, what's basically happened is, because of a principle of light, which is refraction, the prism is basically subdividing light, the main incidence of light, into the different spectrum, into the different electromagnetic wavelengths. And that's here in this very nice chart, you can have an idea of how, what will be their wavelength distance in a way. So, but keep in mind that the combination of all of these wavelengths results in white color. So if we could then recombine all of these rays using a lens, then you will get probably white. Now let's talk a little bit more about color. So what is happening is, so for example, when you see a black object, right? Like it can be a T-shirt or this ball. What is happening is that, so we see it black because every color is being absorbed, right? Which in comparison to a white T-shirt or this white ball, where every color is being reflect, and that's why it appears to us white. Other objects, they might be seen in particular colors, like this red ball or my coffee cup. There you go. And it's just because its surface, it's able to absorb all of the other wavelengths and only reflect the particular color that we see, right? And that'll explain why when we look at the zebra, even though the zebra is made of the same matter, in a way, the variations in the zebra are due to minor differences in the skin cells, where the white portions, they are able to reflect all of the colors, or all of the wavelengths, while the black ones are doing the opposite by absorbing. I found this to be super interesting. So you might be familiar with Banta Black 2.0, right? This is the darkest material ever created, and it's able to absorb light to a 99.96%, which is insane. And this is what the same object will look like if covered completely by this material. And you see, it looks like someone took this and cut it off in Photoshop. So this is what everything will look like if there was no light reflection. So this is what our, for example, this is what the sky would look like if there was no atmosphere to refract, reflect, and absorb light and so on. So we would just see darkness, absolute darkness. Okay. Now let's talk a little bit. Now that we cover, in essence, the classical electromagnetism theory, let's talk a little bit about black bodies. So black bodies are not this. Black bodies in physics refers to objects that are able to emit electromagnetic radiation in all wavelengths. So the sun is a black body because it's able to send radiation in all different wavelengths. As you can see here, a portion of it's visible to us. It's in the visible portion of the spectrum. It's roughly 43% of it. But most of it is in the but we also receive light in the UV and in the infrared portion. Now, why are we talking about black bodies, and why is this important? Well, if we you will see why. So if we have a look at this other example, so a hot piece of metal is also a black body, and because it's also able to emit electromagnetic radiation of all wavelengths. And you might wonder, why is this important? So you see, through observations and experiments, we were able to, or people were able to, in the past, to identify that different peaks in the particular wavelength that is being emitted with the maximum intensity, so it's like the strongest wavelength, their peak tend to shift slightly left as the temperature was rising or increasing, right? So, for example, that explains why really hot objects appear to glow. It's just because they reach a certain temperature that can be maximum or up or more than 5,000 Kelvin. When you reach this temperature, then what you get is a very intense yellow color, right? It's just because they're emitting a lot of this visible light that makes them seem like they're glowing. In the opposite, human bodies, we don't, so our temperature is not that high. So typically will be around 37 degrees Celsius, which translates to around 310 Kelvin, which would be somewhere here. And that's why we don't glow in the dark, right? So, and this has been used, like these observations have been used for centuries, especially blacksmiths, for example. They were able to correlate the color of the object to a certain temperature to know when it was appropriate to, I don't know, submerge the metal in the in water or oil for strengthening it and so on. So what this proof is that color can also be correlated to temperature, and it does not specifically depends on the material, but rather on the temperature. And the problem is, classical electromagnetism theory was not able to account for this. So it had limitations in its ability to describe light and energy. So the math seems to work well for the longer wavelengths of, but it was unable to predict that the intensity will deep down, will make this parabola. So instead, classical theory predicted that this line will continue growing farther and farther and farther and farther into the UV part of the spectrum, which means that it doesn't make sense basically, because it means that in the moment you open the oven, you will be basically be blasted by UV radiation, and we know that is not true. So this contradiction was known in the physics world as the ultraviolet catastrophe. A bit too much for the name, if I may say, but yeah. So what happens when in physics there is something is not working well? Well, some people come and they revisit the theory and they propose new ideas, right? And this is what Planck and Einstein later on did. And again, the idea is not to go super detail into physics, but basically Planck started by saying by introducing his idea of quantization. So this concept of quantization, so basically what he proposes is that the vibrational energy of atoms inside these black bodies, and by extension the energy of the electromagnetic waves that was emitted by them, is not continuous, but it can rather be quantized. So quantized is basically, it means that all energies are multiples of the smallest fundamental unit of energy. It can be subdivided, right? And he called this the Planck energy. This help in combination with Planck constant to fix the math, so that then people were able to predict accurately the distribution of black body radiation at all wavelengths. And then further on, Albert Einstein, while working on a concept to explain another physical phenomena called the photoelectric effect, he rationalized that light should also be made of particles, which he named photon. So photon from ancient Greek means light. So he extended what Planck said about energy, and then he came out with this idea that light must also be made of quanta or photons. So photons are some of their properties is that they cannot be split, only create or destroyed. They're massless, so that means cannot be subdivided, right? And they always move at the speed of light in vacuum, which is roughly 300 million meters per second. Now, why are we talking about this? You will see in a few slides. If we think about a photon, or if you do some research on the internet, you might get images like this one. Further on, if you ask an artificial intelligence to create a picture of a photon, might also get similar ones. Yeah, this dot of light. But the thing is, elementary particles cannot be seen in the way that we observe other objects, and a photon is an elementary physics particle. So we can only see their interaction. So what you're seeing here is a series of pictures taken using a single photon camera, right? And what you see is that they were shooting laser light into a sensitive surface and recording in different frames. So this is just one frame, so just millisecond, then 200 frames, 1000, and so on. So here you can see the laser beam form, but this picture, what you see here is the closest we can see to what a photon might look like. It's just this point. It's just observed as a blink of light from a small point. And this leads back to why I really like this phrase. Yeah, you can only see what it does, but it's impossible to see a photon. So after covering these physics fundamentals, we reached to the conclusion that light exhibits properties of both a wave and a particle. It means that it can behave as both a wave or a particle, which is brain melting idea, principle, or concept that's really, really hard to imagine because you cannot imagine it in the way that you will imagine a particle in real life or a wave. So this is why physics is so hard and so amazing at the same time. But it's just for us to have a better understanding of what it's like. So as a summary, the question now should not be what is light, but rather what is visible light, because that is what we perceive, and that is for what we design for, right? So as a summary, we can say that visible light is the portion of the electromagnetic spectrum that we can perceive, which exhibits properties of both a wave and a particle, photons. It's able to travel through empty space at roughly 300 million meters per second, and it is the basis for the sense of sight and for the color perception. Okay. Now, moving forward, there are three main principles that we also need to understand. And this is how to quantify light. So how do we quantify visible light? So in this chart, for example, let's start with the luminous flux. So basically, a luminous flux is the total emitted visible light from a light source, as it can be the sun, it can be a flashlight, etc. So this is how much light is being emitted in a certain direction, right? And then what we know as illuminance is the total luminous flux that is incident or that is being received by a surface per unit area. So and the unit for illuminance is lux. It's basically lumens, which is the unit for the luminous flux per square meter. So that's lux. So that's how much is being received by the surface. And then lastly, very similar but not the same, we have luminance. Luminance is the light that is being re-emitted off a surface into our eyes or by self illuminance of the object, which can be something that is glowing, like a screen, for example. So the light that reaches our eyes, this is known as luminance, and the unit is candela per square meter. Okay, so these are basically the three essential ways of quantifying light, and then we have a summary here. So once again, luminance measure as the amount of light striking a surface, and it's quantified as in luxes. And then luminance, quantified in candela per square meter, is the amount of this light that is reaching our eyes, which we perceive as brightness. So it controls or regulates how bright we perceive an object or a light source and so on, and can lead into discomfort sometimes, but we will cover more of that later on. So let's talk a little bit more now. Now that we know how to quantify, let's talk a bit more about daylight. So daylight can be basically defined as the combination of all direct, which is the light that the sun is emitting, sunlight, direct light, which can be up to 100,000 luxes perceived on the outdoor horizontal surface, in combination with indirect sunlight. Yeah? Somebody wants to ask a question? I think it was just, no, okay. Continuing, the combination of direct light and diffuse light, it's what we know as daylight. So this diffuse light is solar radiation that is being reflected and distributed in the sky, dome, right? So let's see how to explain this a little bit better. So imagine, as you know, our planet is a sphere. If we only account for the portion of the sphere that is being illuminated by the sun, just to put an example, and we cut the sphere in half, then what we have is a dome. We have imagine a glass dome covering the Earth, and then we have the sun illuminating into this sky dome, and then we have clouds in the atmosphere and particles suspended in the air and so on. And these particles are farther on reflecting light and absorbing it and basically scattering light all over. So as we move closer to the Earth, the amount of this light decreases because the Earth is absorbing most of this light, but the closer we are to the top of this half sphere, it becomes brighter. It will be brighter, right? So daylight also includes the combination of direct and diffuse light that has been reflected by the Earth or other terrestrial objects, like it can be a mountain, for example, and buildings. So buildings, like human-made structures, they also reflect both direct and diffuse light. So let's have a look at some examples of outdoors and indoor illuminances. So for example, if we are at the beach with a clear sunny sky with sun, we might be receiving between 70,000 and 130,000 luxes. Now, if in the same location we cover the sun, so we have some clouds, then what we're getting is mostly diffuse, so it can be up to 25,000 luxes. Under an overcast sky. So this is like a sky that is fully covered, which is pretty much what we have today here in Germany, in Stuttgart. What we will be getting, it's around 10,000 luxes, which differs depending on the latitude, depending on where you're in the planet, but we will see that a little bit later. And then at nighttime, our moon is reflecting back and therefore emitting around 1 lux. That's almost nothing compared to what we're getting from the sun, right? And yet 1 lux is enough for us to find our way in darkness, right? So why do we care about daylight? Well, daylight has many benefits. So it is essential for health and for life in planet and in general. So especially for the production of vitamin D in our bodies and other metabolic functions. So for example, nowadays that we're in the mid starting winter here in Germany and days tend to be more cloudy and less sunlight. It's really important to take this vitamin D as a supplement, as a pill, because we're just not exposed to enough sunlight, and this can lead to some health problems, like you might lose some hair and so on. So that's why sunlight is really important. But daylight also controls day and night rhythms. So this is known as the circadian rhythms, and these are basically you can think of it as if each one of your cells in your body has an internal clock, an internal watch that is related to day and night rhythms. And this comes from evolution from millions of years ago. So, and that's why sometimes you might not know exactly how, but you can tell what time it is with a certain affair within a fair range. Um, so it's just because our bodies are made of these cells that they have this internal watch. So they're really important for metabolic functions. Um, Also has a lot of physiology benefits, like that they increase our well-being. They can increase the attraction of a certain room, and of course our productivity. And then definitely energy-wise, this is free energy with almost no losses that we are receiving. So in fact, and this might sound like something very clear, and it makes a lot of sense that we want to use daylight, right? But nonetheless, around 20% of the electricity that we use worldwide goes to artificial illumination. And only in Europe, this number is around 14%. So, which is definitely we could work on reducing these numbers. And then keep in mind that daylight, we perceive, so around 70 to 80% of our perception of the surroundings happens with our eyes. So that's why daylight is extremely important. Um, so what is visual comfort then? So we can tell that space with where we might be in visual comfort is that space that receives sufficient daylight that comes free of any disturbance. So it's not excessive. We don't suffer from glares, or it's not too little. That can cause some headaches and other problems. And also it's a space that is so well illuminated that can also bring information from the outside. So the contrast between outdoors and indoors luminance is not that high, so that we can look at the outside without any sort disturbance, and we get information about time, about our surroundings, weather conditions, and so on. And also that we get enough light as to properly render color. Uh, in our eyes and brain. So the opposite of this will be visual discomfort, which is what happens. So the one of the clearest form of visual discomfort might be glare, which happens when you look straight at a very bright source of light, as it can be a window, as it can be looking directly at the sun, or even conditions where you don't get enough light and you have to focus and you have to really squeeze your eyes into getting information. This can also lead to headaches and other health problems. So, but naturally, the conditions or the requirements, the light requirements that we need differs according to different tasks and different spaces. So just to put a few examples, in a working environment, the requirement is around 500 lux. That's enough to work without any problems and have the nice boost of productivity that we all need. But for reading at home, between 100 and 200 lux is generally okay. And for example, for circulation areas, 100, 150 lux is also okay, because these are spaces where we do not need to perform like highly demanding visual tasks, just walking around, just finding our way, and so on. So it's very important to define the task in order to design considering light. Now, just as a summary, um, we always need to consider, like I was saying, indoor daylight requirements, and make sure that the illuminance levels are within the indoor comfort range, and also to allow for that nice transition between indoor, outdoors, and so on. So um, before making a short break, let's talk a little bit. So how do we measure light? So we know that it is important. We know what it is now. We know what is visible light and daylight and so on. So in order to be able to design with it, how do we measure it? So most of the times you might need special equipment. If you go to a place and you want to measure how many luxes you might be receiving in a particular area, you might need special equipment, like it can be a lux meter. But these can be a bit expensive. They can be a bit expensive, and other, especially other kinds of equipment can go further in the thousands, and so not everyone have access to them. It doesn't really, unless you're this is your daily work, and so on. There are also apps that can give you an idea of how many luxes you might be receiving, and this app, especially because our smartphones, they're evolved enough as to have all of these sensors. So there is this app, for this Lumo light meter that I have on my phone, that it can give you an idea. So, and it is for free. You can find it both for Android and iOS. So it might be fun for you guys to download it and go checking in your at home or at uni. You can check in your desk how many luxes, and see if it matches with the requirement, how much you should get. Um, but thankfully, we have computer-based simulation that we can implement in order to, in a very, so it's definitely cheaper, and it allows us to cover with multiple sensors entire spaces, which otherwise in real life you will have to place one of these special device every I don't know, every 1 meter or so to cover a room, which is physically impossible, or not impossible, but very, very difficult. But this we can do very, very easily with computer-based simulations, and in general, like worldwide, but in particular at Transsolar, we use a lot Rhinoceros 3D and Grasshopper as the user interface, and especially the Ladybug and Honeybee plugins, which allows us um, to set all the parameters and to assign all the geometries from our 3D model and so on, and to convert this in a way that a validated engine, in this case Radiance, which we have been using for over 30 years now, can perform the daylight simulation. So Radiance is a scientifically proved, validated engine, which is it can perform static daylight analysis. And then further on, if we combine these two, right, we can also take advantage of further developed plugins or software that is able to take Radiance basics and implement it in a smarter way or faster way, and they're able to produce dynamic daylight analysis, like for example Climate Studio from a company called Solema. We have been using a lot in the last 2 years because it's extremely fast and flexible and so on. So these softwares, they are not free, unfortunately. But for example, Grasshopper, it's part of Rhinoceros since version 5, I believe, and Ladybug and Honeybee, they are free plugins, but you do need a license for Rhino. So That's a bit of a downside. Radiance is free. Climate Studio is it's also paid. You need to pay for a license, and it's a little bit expensive. But everything you can do with Climate Studio, you can definitely do with this too. But there are some free online tools, like you already saw from previous lectures. You were introduced into the Andrew Marsh tool. Only that in this case for daylight, I encourage you to definitely try the dynamic daylighting tool, and also maybe the sky generator and the dynamic overshadowing tool. So, but mainly the dynamic daylighting tool. It's really nice. It allows you to take an example room and to change the position of the windows and so on, and see how this impact has an impact in daylight, um, in both daylight factor and more dynamic simulations, which we will cover in the next slides. But let's first take a 5-minute break, and then we continue with the introduction to metrics and simulations and so on. Okay, Clara?
Yes, that's perfect, Daniel. I will interrupt the recording for 5 minutes, and then we see here at, for us, it's 10:20. For you guys, I think it's 11:20.
Yeah, perfect.
Thank you, Daniel.
To you. Okay, see you guys in 5 minutes.
The stage is yours, Daniel.
Thank you. So hi, everyone. Welcome after this short break. Now, let's continue with the presentation, which is so some of the tools and some of the ways that we can measure light. But then moving forward into the computer-based simulations, I would like to introduce you into some of the most widely used or important simulations or metrics that we perform or work for here at the office, but in general. And I would like to start with daylight factor. So daylight factor was firstly introduced, I believe, in the 1980s as a metric that it is. So what daylight factor does is that it assumes a point in time, right, a moment when the sky is overcast. So as you can remember from previous slides, when we have a fully overcast sky, the total amount of illuminance that we get in the outdoors, it's around 10,000 lux, right? So what daylight factor is doing is it's finding the relation between the external illuminance, this 10,000 lux, and the internal illuminance that can be measured indoors, right? And then we get a percentage, which means that if outside we have 10,000 lux, and inside we measure a daylight factor of 3%, that can relate to 300 lux, right? It's 3% of this 10,000, and we get 300 lux. And the reason why this metric is being used so much is because it is a simplified metric, right? Which is useful only for preliminary design. So since it is simplified, it's faster. So it's really faster to perform these simulations, and they're good to give an idea of how a certain room or space might perform in terms of daylight, and to allow us to play with different variants to see quickly what the effect might be. And also, since we're considering a fully cloudy sky, so the sun is out of the equation in a way, so we're not accounting for direct sunlight, only for diffuse, and that means that it can be applied anywhere in the planet. So it doesn't matter where you are, you can use a daylight factor simulation, which compared to other dynamic metrics that we will see later on, allows us to do this anywhere in the planet, and to have a way to it's something to compare in a way, so you're not limited by the location in the plant. So, and in a way you're also evaluating a worst case scenario, which is what you will get if you have a fully cloudy sky, right? This is the worst thing that can happen during daytime besides an eclipse. but we don't have eclipses. Thankfully, we don't have them so frequently. But on a normal day, this can happen. So if we're able to check how well a certain space performs in terms of daylight during the worst case scenario, then we have a guarantee that when the sky is clear, it will definitely perform better, right? So that's some of the reasons why we use it. And then if remember when we saw some of the requirements, for example, in a classroom, remember we said the classroom or workspace, we refer to 500 lux. Well, in this case, it will be 5% data factor. Or it can be also 3%. So it's in this range. Ideally, you will get 500, but starting from 300, it's okay. And then circulation areas can be around 1 to 1.5% daylight factor. If we go back here, daylight factor is also giving us more information. So generally between 2 and 5%, we get good illumination. So artificial lighting is almost not needed during the entire day. And we find a good balance between daylight and thermal comfort, because as you know, sunlight is not just visible light. It's also carrying heat and energy, or energy in the form of heat, and this heat entering the space can warm up the space, and this is what we call a thermal load, right? And now smaller than 2%, we start having problems because there's just not enough light, so poor illumination, and therefore we need to turn on the artificial lights. And higher than 6% in terms of daylight is very good, right? But there is a risk of overheating of the space because of the increased thermal loads, solar gains, basically. Okay, so this is generally these are good numbers, 2 to 5%. Now moving forward, remember how I said, like under an overcast sky, we will receive around 10,000 lux. Well, this number was agreed. It's worldwide agreed as a standard, but in reality, um, this value, the outdoor illuminance, depends on the latitude. So depending on where you are in the planet, you might get more or less. So that makes sense. So if you're closer to the poles, you will get very little. So you will get around 3,000. It's just because most of this diffuse radiation is being absorbed by Earth itself, and that's why these places, this in combination with the poor, like also reduced direct light in these areas, that's why the poles are so cold, right? But now in terms of daylight, this also makes sense. But then on the opposite, as you move closer to the equator, this number can be significantly higher. So it can be up to 18,000 luxes. Now, in your case, Zimbabwe, it's right here. So in your case, you're fine. You're aligned with the universal standard. So 10,000 lux. It's good to consider, even though if you are more precise, it should be something a little bit higher, like 11,000, maybe to 12,000 luxes. But in general, 10,000 it's a good metric. And then here is another example. This one I did it yesterday using the Andrew Marsh tool, just an example room with a couple of windows, performing daylight factor simulation, where you can see areas really close to the windows. They can get daylight factor values above 6%, which translates into more than 600 lux, while these deeper areas of the room with no daylight access, they receive less than 2%, which is equal to 200 luxes or less. This is wrong, less. Okay, now another metric that is widely used is point-in-time illuminance. So point-in-time illuminance, what you get as a result is not a percentage. You actually do get luxes. You get illuminance values. It's basically measuring the amount of light that is falling and spreading over a given surface area. So we take a room, we do a point-in-time illuminance, and we will get the lux values at a given date and time. So this is also, like the name says, is a point in time. Also as in daylight factor, where you do not account for any dynamic peculiarities of lighting, like movement of the sun and so on. In this case, it's also a moment, so in a specific hour and minute and so on. Only that for performing this study, you can account for the sun. So we don't assume a worst case scenario, but rather you can define a specific sky type, which can be a clear sky. It can be a cloudy sky. It depends on what you want, but you do it for a moment, right? So moving forward into an example, this is from an evaluation of a project here in Germany, and this is a point in time um, simulation for the 21st of March at 12 o'clock, so noon. And what you're seeing, this is an atrium. So imagine you take an atrium and you open it in the same way that you will unfold the box, right? So what we're seeing here are the walls, and this is the atrium. So this way we were able to calculate how many luxes we will receive on the floor and on the walls. And these particular shapes that you might be recognizing here is just because of the way the enclosure of the atrium was built. So this relates to, and in combination with a specific, like the sun position and angles and so on, sun incident at the very specific moment in time. And this was performed, of course, for considering a clear sky. That's why you can see that in this world, for example, we're getting a little bit more than 10,000 luxes, right? While in other areas that are not lit directly by the sun, we get significantly less. And the last one of the metrics that I would like to share with you, and remember there are many more, but these are some of the most important ones, is daylight autonomy. Now, daylight autonomy, it's also a percentage, but in this case, it's the percentage of an occupancy time within the year, right? In which a minimum illuminance threshold or requirement it's been met. Generally, like as a standard, we take 300 lux. So that is being received at the working plane. So typically the working plane, if you're analyzing an office, you will assume that this working plane will be between 76 and 85 centimeters. That is the height of a table, right? That is the height that the table will be. So therefore, that's your working space. That's where you will have your notepad, you will have your keyboard and so on. So that's why we do not measure it at the floor, because you do not work at the floor level, unless you're designing, I don't know, a kindergarten, where maybe instead of 85, then we check 20 centimeters or so, because kids tend to be more close to the ground and so on. So it really depends, but in general, for working spaces or studying spaces, the assumption for the working plane is in this range. So recapping, because I think I talked too much about the working plane, it's the percentage of the occupancy time, defined time of the year, in which the minimum illuminance, so this 300 lux, is at the working plane, is satisfied by daylight alone. So we only account for daylight here. So for example, having a daylight autonomy of 70% in a room means that the use of artificial lighting will only be necessary for the remaining part of the time, so 30% that the space is occupied. So it's important to notice that we do not perform this evaluation for the entire year. We only do it for a defined schedule, which in a working space could be from 8 a.m. to 6 p.m. For example, it can be 9 to 5 also, but in a residential project could be completely different, or in a very particular space can be maybe just in the morning. It's really only the time that the space is occupied. It doesn't make sense to include nighttime or other moments where the space is not being used, like on the weekends, for example. So it's important to define our occupancy time. And now the main difference, well, there are many differences, but the main one compared to daylight factor and point-in-time illuminance evaluations is that daylight autonomy involve understanding of how the entire building is affected by the dynamic nature of daylight through the year. So in daylight factor, it doesn't matter the orientation of the building, because the sky, the light that has been distributed by the sky is uniformly distributed all over. So it doesn't really matter. There is no direct sunlight. So it doesn't matter how your building is oriented and so on. Like neighboring buildings, they do have an impact because they can block diffuse light or emit or reflect diffuse light. But in general, you do not care about the orientation. But in daylight autonomy, you do care about the orientation. So daylight autonomy is actually more accurate. So it's more precise because it accounts for the entire year with different sky conditions and so on. But it takes longer to simulate. Nowadays, with Climate Studio, for example, that I mentioned before, with engines like this that take better advantage of radiance and so on, they have become very fast. So you can perform these simulations really fast. But if you're using Grasshopper, Honeybee, Ladybug, or some of the older versions, it can take up to days. So imagine before in our office, we will start doing a simulation. We will set everything, the parameters, and click run and go home. Come the next morning just to find out that your simulation is still running without even knowing how further along it's gonna take. It's insane. Now with these new tools, we can run it and see it in real time as it evolves, and it's a matter of minutes. So, but this is also a reason why daylight factor is so commonly used, especially at the initial stages where you just want to explore different variants. Now, this is an example of daylight autonomy simulation, but daylight autonomy doesn't come alone. Daylight autonomy also comes with spatial daylight autonomy, which we know as SDA. So they're related, but they're not exactly the same. So because spatial daylight autonomy describes the percentage of the analyzed floor area. So daylight autonomy refers to time, so percentage of time where a certain threshold is being met, while spatial daylight autonomy describes percentage of the analyzed floor area or area in general that is receiving at least this minimum threshold that we define as 300 lux for at least 50% of the annual occupied hours. So in simpler terms, we might say that spatial daylight autonomy is just the percentage of the floor area that has a daylight autonomy of 50% or more, right? Of at least 50%. So what you're seeing here is an example of an evaluation we did some time ago for an existing building. This building I included in the examples. We will see it later on. A building, it's called Lustenau 2226. And this building performs amazingly well in terms of daylight because it has uniformly distributed windows all over. Also, like the depth of the floor is not that much. So I believe it's around 30 to 30 meters. So it just has enough daylight access. And in this simulation, you can see the daylight autonomy as you will get it in percentage. So you can see everything that is above 50 is considered to be great and above the target. So all of these areas, you may rarely need to illuminate them with the use of artificial light. While on the other hand, you have, we're basically filtering these results into only two colors. So everything that is less or more than 50%. And this is a clearer way to see SDAs, which just means that X percentage of the floor is above the target, and that's what we can first see. As you can see, core areas, they're below because they're walls, and of course the daylight will not reach that far. But in general, close to the facades and working areas, it's great. Okay. Now that we cover some of these metrics, let's take one step back and talk a bit more about light and its behavior.
Daniel?
Yes.
Sorry for interrupting. Just one second. I just want to remember that we have 30 minutes left for the end.
Perfect. Thank you, Clara. Okay, let's speed up. Let's speed up a little bit. Let's talk about some of the light properties before getting into examples and design strategies. So, light can behave in very different ways. These are some of the main, probably just the main. Light can be transmitted, can be reflected, can be refracted, diffracted, absorbed, and scattered. Right. Now let's have a closer look at some of these. So reflection, it's basically when light bounces off a surface, and there are two types of reflection. It can be specular reflection, which is when a light is being reflected by a very smooth surface that so that very little of this light is being absorbed or none, and it's been reflected in a certain way that we will cover in the next slide. And it can be also diffuse, which is what happens when light is reflected from a rough surface. So moving forward into specular reflection, what is happening is that if we imagine light, so we already said like light behave as a wave and as a particle, but now I'm going to ask you to abstract a bit more and imagine light as a ray, right? So if we shoot a light ray into a surface that is, and we get specular reflection, what is happening is that basically light will be bounced off with the same angle, but opposed to the surface normal. So this is what happens, for example, when we look at self in a mirror. So a mirror is a good example of specular reflection because we get a clear image of ourselves or what will happen in a very still water body. And the opposite, diffuse reflection, is basically what happens. It's that light has been bounces off in many different angles, not just in the same angle, opposite, but same angle, but it's been scattered into multiple angles. And this is just because of some of these surfaces have a rough structure, like it can be a piece of paper. So you see what it looks like. So it's not smooth. It's not bouncing in a specular way. This is a nice example of how this effect can be used into architecture. This would basically, it's happening. These panels are there is a skylight passing through the middle. We will see this as an example before, and then these reflecting panels are bouncing it off, and then the curved roof is uniformly distributing light. Then we have transmission, which is basically the amount of light that is able to pass through a medium, or it can be a glass, for example, and keep traveling without being absorbed, right? So a very clear glass has a very high transmission, while a darker glass has a very low transmission. So we call it usually you found it as VLT, this value. This just refers to visual light transmissions. And there is also transmittance, which is not the same, because this one refers to the amount of light energy that a medium can absorb, reflect, and scatter. So if you know the transmittance value, then you can calculate the amount of light that it will disperse, this material will disperse, or its ability to block or absorb photons of light. Refraction is the process in which light changes direction or blends as it moves from a medium to another, can be from air to water. And this is the same principle that allows us to split light into the different wavelengths and see colors by using a prism, or the principle behind this effect when objects seems to be larger or distort under water. And is also responsible or involved in some of the most beautiful phenomena that we can observe in nature, like rainbows or solar halos. The materials or mediums, they can also have different properties. So they can be transparent, can be translucent or opaque, depending on how much light they let pass through, or how light behaves while passing through them, and therefore how clear we see through them. An example of a transparent material can be fish tank or a very still body, water body. So basically, they transmit almost all light passing through them, and you can see clearly through them. Okay. Then on the other hand, translucent, they allowed most light to pass through them, but light is being scattered in many directions, so we don't get a clear image afterwards. So they objects, they're seen blurry through them. And in this example, a medium doesn't necessarily needs to be something more widely understandable as a translucent material, like it can be frosted glass. It can also be fog or smoke particles suspended in air, because they're also scattering light. And the reason why we see here beam of light is just because these particles are scattering light in many different directions, and some of that light they reaches our eyes, or a camera in this case, and that's why we see the cone of light. And lastly, objects, they can also be opaque, means that they reflect or absorb light, but they don't let any light pass through. And of course, they cast shadows. So that's one of the easier ways to identify an opaque object, and it's just because of their structure, can either absorb or reflect. Right, some examples can be wood, metal, stone, or any other solid material. Now, sorry, I'm going a bit faster now, but it's just because we have very little time. I just want to show you some, there are many, but some of the design strategies that can be applied, and this will come combined with some rules of thumb. The idea is that we get a first introduction, but that then later on you can refer back to the slides. You will have the slides, I guess, so you can revisit because there is a lot of information in them. So basically, there are we can say there are three types of design strategies. I just divided them in this ways for the lecture. We can have side lighting, which is when light is coming from the sides, from vertical openings on the walls and so on. Top lighting, when we get light from above, and combined strategies. Okay. So inside lighting, typical example windows. There's not much more about it, right? So we have the window, and logic says the larger the window. Like a good friend of mine, an ex-colleague, used to say, the larger the window, the more daylight. It's as simple as that. But there is a very nice rule of thumb that can be applied, which is the window head height rule of thumb, that says that in a side-lit space, space with a window, with a standard window and blinds, the depth of the daylight area usually lies between 1.5 and 2 times the window head height, which means that basically the height of the top of the window multiplied by this number, they will give an indicator of how far light, like good daylight, will get into the space. If the space does not have shading, like these Venetian blinds, then it can be up to 2.5 times the height of the window, which means the higher we place the windows, the deeper daylight will reach. Now, there are further strategies that can be implemented for getting deeper into spaces, like light shelves, right? The light shelves, they can be external or they can be internal. And basically, they are horizontal surfaces with a high reflectance material that they bounce light farther into the ceiling, and therefore farther deeper into the space. As you can see in this example, these are internal light shelves. Now, this is a bad example because there is an object like this duct that is blocking the light that is being reflected into the ceiling. This is supposed to go on the ceiling, but this is being obstructed. So this is a bad example. Now, similar to light shells, but distributed more into the vertical space, you can find you can have louvers or overhangs, and basically this can be opaque, or this can be of a material that is being perforated, right? So you can have different types of opacity on them, allowing for more or less light to come in or for bouncing more. So as a general rule, it's recommended that this opening percentage, it's low at the top floors for high light reflections, and high at the bottom floors for maximal light transmissions, but it really depends. And I put together this slide that summarizes different types. So they can be horizontal, but they can also be vertical. And so in this case, they also, so of course, they also act as shading. I think you covered this before with Clara and Matthias for the radiation lecture. But they do have an effect on daylight. So it's important to consider this duality on their effect. So again, we're short in time, so we will just skip, but you can refer back to these slides in the future. Oh, this is okay. Now, top lighting. In top lighting, and I wanted to put more focus into top lighting because I believe in same hour because of the solar angles and so on. I think you're more exposed to high altitude sun angles. So therefore, I think you could benefit way more from the top lighting strategies, and in general, top lighting strategies are great ways to lit spaces. So we can there are many different ones that can be categorized somehow into skylights, sheds, lanternins, domes, atriums, and solar tubes using devices. So let's go through them. Skylights, they are basically horizontal openings in the roof. They allowed for direct entrance of natural light into deeper areas of the building. Typically, they are not clear glass. They're more of translucent glass so that we can take advantage of this diffuseness of light and reaching a more uniform, and also avoiding some solar gains into spaces. And that's also why they should be used with care, right? You should not have a fully uh, let's say like a very large skylight, because then you can get into problems. You can increase the internal temperature of spaces, and there's this very nice example of Villa di Carval and their skylights, right? So as a rule of thumb for skylights, particularly different light strategies, they can lead to various daylight environment. And you can see what is really important is the sizing and the distribution in space of the skylights, so you can reach different. So strategically placing them is very important. As another important rule of thumb, this one allows you to define or calculate the correct distance between them so that you have an homogeneously lit space underneath. Or to get a proper daylight sun space, you can look at the skylights horizontally by 1.5 times the floor to ceiling height. And then you can also separate them from the facades by 0.5 times the floor to ceiling height. This way you can achieve a uniform daylight distribution on the spaces below. Sheds are basically based on the sawtooth geometry of the roof. So we're tilting the roof, and then we have these vertical or incline openings, but basically this tilting can be used to achieve certain conditions inside. It can be either for blocking direct light or for allowing more light to go through by bouncing on the surface. Typically, the sheds are oriented to the particular orientation that does not receive direct sunlight. In the northern hemisphere, it will be north. In the southern hemisphere, it will be south, right? They're typically used in industrial or big buildings like a hospital or a warehouse and so on. Lanternings, similar but not exactly the same, because they are basically formed by opening that they protrude a bit in relation to the roof, and they tend to be smaller in a way and only go into two directions, but they're also a good way to illuminate. I've seen these many times in theaters and so on. It's quite common there, and they also, if you combine this with operable windows, let's say, or with having the option to open them, you can allow for cross ventilation, which is natural ventilation, so which is always great to have. Domes are another example, and one of iconic example is the Reichstag dome in Berlin. Because basically they allow for a lot of daylight to get in, because you're basically maximizing the view of the sky, right? But this is also a problem because it can lead to overheating in the spaces below. So that's why it's recommended to use domes or combined with areas that are not so sensitive, let's say, like circulation areas, or maybe courtyard or center areas and so on. Definitely not for working or spending too much time underneath. And then one of the most important ones are the atriums, right? Just like skylights, atriums open directly on the roof, and they often have this pyramidal or gable shape, of course, built with metal profiles and with a glass or the diffuse glass closure, clear glass, and so on. These are recommended for buildings when you have a greater number of floors. So um, like high buildings and so on, where you really want to find a way to illuminate core areas, or when you have a very deep floor plan, then it's always a good idea to cut a hole in the middle and have an atrium where you can benefit from daylight from both the atrium and from the outsides, right? Now, for the atriums, there are a few rules of thumb. The most common one is the atrium rule of thumb that says that in a fully daylit atrium, the maximum atrium height, so the maximum height, is less than 2.5 times its width. So just by applying this rule, you ensure that uh, even the bottom floors, they will have enough view of the sky, so and which transmits into having daylight access, basically. Atriums can have different shapes or structures. Elongated atriums is always better to distribute them along the long axis. So basically the long axis runs from east to west. That way you're maximizing the lighting coming from either north or south, right? Stack atriums, there's also the lower floors should be less wide, and then you can increase the opening as you move upper, again just to maximize the view of the sky and increase daylight. And then for square atrium, it's basically the rule this rule that we cover first. Lastly, from the top lighting strategies, we have solar tubes, and these are basically tubes that are internally coated with a highly reflective material. They can also be made of fiberglass. And what they cause is that they generate different light intensities. So it offers a lot of flexibility and also allows for daylight to reach areas that otherwise it's will not be possible, right? They can be installed in different types of roof, can be flat or inclined, and they can also be flexible or rigid. Here we have the BPRI library by Alvarado, which is a great example of their use. So, and last but not least, let's talk about materials. Since materials, as you know, they have an influence on how we see color, but also on the properties and ability of bouncing light. So generally, it's a good idea, and it's always a good advice to use highly reflective materials for key elements of the building, such as walls, ceilings, floors, and so on. In this example, this is Lustenau 2226, the example I show you for daylight autonomy, where, as you can see, the interior surfaces are very bright. They're on the white side, right? And that helps for light to bounce. Just see up here, in the ceiling, how much light is being scattered. And most of this light is actually bouncing off the windowsill because they have a thick wall. So this is a fantastic example of a good daylighting performing building. So always a good idea to go for highly reflective materials. So let's go through some examples of, now that we have covered, I think, most of the necessary principles and so on. Let's see a couple of examples where daylight strategies have been properly applied, and we can go through history, and there are the example of the Turkish bath, in this case hammam, where you have these little narrow holes in the dome that allows formations of light beams or spotlights in the floor, and this phenomena can be observed in nature. This in particular is called the Komorebi effect. Komorebi is Japanese for light that passes through trees and forms beams in a way. So and the reason why we see the beams again is just because there are floating particles in the air, that it can be dust, it can be water vapor particles, as it is the case of the bath, right? And that's why we see the beam of light. Otherwise, we will only see the dot in the floor. And there are fantastic examples of this principle being used in architecture, like this library in Gandon, Burkina Faso by Francis Kere. So it is placed between the equator and the tropics. So it made a lot of sense to get this top lighting strategy. So in the form of very little skylights, and they were made with terracotta pots cut, and some parts are concrete, like the floor. It has this shape. And the roof is also ventilated. So they have this in other parts of the building. They have this ventilated roof that protects the open skylights from rain, and allows for natural ventilation, right? And at the same time, it's shading from the sun. Other examples of a similar approach, it's the Louvre Abu Dhabi, by Ateliers Jean Nouvel in collaboration with Transsolar, where the same principle was approached, and then it was really important to get a right balance between contrast and visibility, dust and twilight, and then to consider the divergence of sunlight, calculate divergence of sunlight, to determine which one will be the minimum size of the openings in the dome, so that we could get these light dots on the floor. And this is an example of light being used for creating a more serious environment, which was the intention in this case. And for this project, a mock-up, like a real size mock-up, was built, because it can be really tricky to design with light, and to achieve this particular effect, it was necessary. So there were a lot of mock-ups being built for these at smaller scales and so on. But yeah, I think the result looks amazing. Now, other examples of top lighting, it's the High Museum of Art edition. So as you can see, there are almost no shadows in this space, and this is because daylight is being perfectly diffuse and stable, and there is a minimal influence from sun and direct radiation, which has been, this is thanks to the skylight pipes on the roof, which were cut according to the sun path on summer solstice, for example, 21st of June, to block, not to block, but like to collect direct light, and to further on diffuse it to the inside, so providing exclusively diffused light all year. As you can see in this sketch, you see how it's being collected and then bounces on the internal surfaces, and then gets diffusely distributed inside the space. I really like the fact that they include this area in the sketch, and later on they made this picture. I think it's a great example of how well this space performs. See how equally distributed light is in here. The Kimball Art Museum, which we already seen, So as I was telling you before, the way it works, so it is inspired in the Roman architecture in a way. Louis Kahn, he was a master of light, of daylight, and basically what is happening, you have this skylight here at the skylight line in going through, and then light bounces in these parabolic reflectors back into this tilt like curve roof, and what you're getting is perfectly diffused homogeneous daylight, which is not exempt because sunlight is very tricky. It's not exempt from some direct beams of light passing through space here and there. Um, Another fantastic example comes from Mario Cucinella Architects. This is the Santa Maria Goretti Church in Calabria, and one of our colleagues, Alberto Bruno, he worked in this project. He worked for them before, and it's an amazing example of how light can be distributed inside the space. They took their inspiration on the Northern Lights for creating these PVC made curtains, like hanging curtains. And as you can see, it only takes really small skylights heating these materials, which are later on diffusing light farther inside the space. And as it happens with the previous example, sometimes you get direct light hitting the space. Another example, this one is a Transsolar project. Project Transsolar was involved in, where we had this building that needed to be day lit, but it was within a dense urban fabric. So a vertical corridor was designed to allow light to enter and then bounce farther into the wall, so that this way sufficient light can penetrate even to the depths of the building complex, right? And at the same time, this was also serving as a solar chimney for exhaust air extraction. Here we have a picture of what it looks like, even though we have some, I believe these are also, it look like a bit of artificial light, but in general, you can see a massive daylight contribution from this strategy. Another example, so imagine a light shelf, but at a massive scale. That's what's happening here at the Herning Museum of Contemporary Art in Denmark, where you have these vertical skylights in the upward curving roof, providing natural light to the space, and then light is bouncing off this other in the gallery roof and farther and equally distributed. So similar effect, but at a bigger scale. Speaking about materials and the importance of using highly reflective materials, we have the Butaro District Hospital. Yeah, it was this building was constructed using local materials by local craftsmen. So here you can see that even with local materials, it's possible to achieve these sort of super well lit spaces, and they're also very important because they involve the community into the building process, and they share a lot of love for this building in particular. They call it their castle. So I think I found that to be very inspiring. Again, this is now 2226 in Austria. We have seen this one before. You just have a look at the corridors, and something that is also very important is for these spaces to be open spaces. So without having too many walls and divisions in between, so that light can play through space as it wills. Yeah, this is a view from the outside of the building. And side lighting strategies can be further implemented or scaled to this extent, as it happens at London's office for the Foster and Partners headquarters, where you can see they have this massive window facing north to the Thames River, and basically what they're getting is a lot of diffuse light and almost no direct light. I believe this picture was taken in the late afternoon at the sunset. So it's beautiful and very nice working space. You can see how deep light, good daylight reaches into the space. In educational architecture is extremely important also to have well-lit spaces, right? So because activities performed during daytime, they have strict daylight requirements, right? So that's why it's important to design with care, the same way that you will design a passive house building, right? This is a great example of that, where you have this side lit kind of like skylight, like a shed in a way, adding from the top, and then you also have some side lit strategies from the windows. It is really important, and this also allowed for cross ventilation, right? So it's daylight and cross ventilation, which is great. And lastly, the last example, coming to also, this is also a project Transsolar was involved. So the Transsolar buys on the envelope of the cancer research building in Switzerland, right? So the idea was that sufficient daylight should be able to penetrate the depths of the room, but at the same time to do not dazzle them, so that you don't get too much. And the sun should not bring too much heat into the building as well. So the idea was to use these shades that are perforated, with different degrees, and then through parametric design, multiple variants were considered and leading to the optimal variant, which was then built. Here you can see how some of these radiation is being bounced back, or light is being bounced back, while good levels are reaching the space, and it looks, honestly, it looks amazing. It's quite a nice example. Yeah. So with this set of examples, I believe we've reached the end of the lecture, which was intended to give you a brief introduction into light and daylighting strategies, daylighting delivery strategies. Unfortunately, we do not have the time to go deeper in detail. Would love to, because this is a fascinating world, and there's so much more that we can talk about. But hopefully, this was enough to get you excited, to inspire you in a way, and to just for you to feel the need to maybe do some more research or to get more involved in this beautiful world of light. So thank you very much for the opportunity. And now we can, I believe we have roughly 10 minutes. No, I believe we're right out of time. So maybe one or two quick questions, Clara.
Yes, Daniel, thanks a lot for this great and inspiring lecture. That was really amazing. I would invite all the students to maybe turn on your camera and raise your question, because this would be the right moment to do so. So please go ahead. Not only the students, but maybe even the professors, if you have any curiosity or any questions that you want to address to Daniel, please feel free.
I think they're tired after an hour and a half of daylight. That's fine. If you don't have questions at the moment, then please, if they come later, please just forward them to Clara or me, and I will be happy to get back to you with an answer, or just take it as feedback for future lectures preparation. So, and yes. I also believe we exceeded the time, right? We're right on time. So Clara.
Yes, I sum it up. So once again, Daniel, thanks a lot for this lecture. Thanks to all the participants for attending. And just as a reminder, you will receive a survey from me this afternoon, in that I really ask you to take care and to reply as soon as possible, because it's really important for us to receive your feedbacks in order to know if you like the lecture, if you knew already some contents, if you would like to change something, or if you have any extra comments that you want to give us. This is extremely important. So once again, thanks everybody. I wish you Well, Daniel, to you, I wish you a great day. And to all the others, we see each other again this afternoon because we have the last lecture. So I hope you are not too tired and have a nice day.
Thanks,
Bye-bye.
everyone, and bye-bye. It's been a pleasure.
Thank you.
Thank you so much.
Thank you.
Thank you.
Thank you.